A sequential machine uses registers to manage when combinational logic values change. The outputs of the sequential machine depend on both the primary inputs of the machine and the values of its registers. To be sure the sequential machine works properly, we manage the structure of the machine, the timing of signals into the registers, and the properties of the clock. A basic requirement on the structure of the machine is that the combinational logic can't have cycles. This NAND gate's output is connected to one of its inputs. The NAND gate performs a logical inversion, so the output oscillates even when the other input doesn't change. Not all of the cycles may be as simple as this example. Complex logic may contain cycles that aren't obvious. A timing diagram shows us requirements on the characteristics of the clock signal. This register is designed to use the rising 0 to 1 transition of the clock as the event that causes it to save D's current value in the register. The register's data input stops changing in time to satisfy the setup time. That's the time required for the input signal to be stable before the clock event. The data input starts to change again after the hold time, the time at which the clock event when the input signal needs to remain stable. The clock period is limited by the delay through the combinational logic. The worst case delay through the logic, the critical path, is the delay from any input to any output. There are 3 paths from A to each of the primary outputs, X, Y, and Z. But A is only one of the primary inputs. There are also paths from B to Y and Z, and from C to Z. Any of these paths could be the worst case. The fastest possible clock period T of the machine is the sum of the combinational worst case delay, the setup time, and the hold time. If any of these parameters is violated, the machine may produce wrong values. A long clock period corresponds to a low clock frequency, so we're interested in optimizing all parts of the system to maximize our clock frequency. The clock is a special signal in the sequential machine, and we place strict requirements on how it behaves. In a basic sequential machine, all the registers are controlled by the same clock. The worst case delay for all the logic in the machine limits its clock period. We expect operations in the sequential machine to happen synchronously. This means that the clock signal should arrive at all the registers within tight tolerances. The clock signal, like all signals, is analog. We require the clock to be of high quality with only small deviations from its ideal waveform. Imperfections in the clock signal can come from many sources. The resistance, capacitance, and inductance of the clock wiring and associated circuits can introduce delay into signal transitions as well as noise. These circuit elements can also couple to other signals in the clock, injecting crosstalk that distorts the clock signal. Electronic phenomenon can also introduce random noise. We can describe registers in sequential machines in hardware description languages. This is an example of a register in the Verilog HDL. The always statement tests a condition to determine when a statement block should be executed. When the clock signal transitions from low to high, creating a positive edge, the data input is copied to the output. Here's a register model in Verilog based on the always construct and the schematic that's generated by hardware synthesis. The register transfer machine gets its name from its structure. This simple example register transfer machine has 3 registers forming a rank that feeds a combinational logic block. The outputs of the combinational logic feed another rank of 2 registers. More complex register transfer machines can be made with more ranks and with feedback. Here's a 2-bit shift register, a common sequential machine. As 1 bit comes into the shifter, the earliest bit comes out of the other end of the shift register. A counter is another useful sequential machine. This counter is specified as a register transfer machine with an adder and registers for the bits of the value. The carry input to the adder controls when it increments. When increment is 0, a 0 is fed into the counter, resulting in no increment. When increment is 1, a 1 is fed to the counter, resulting in an increment. The carry out of the adder provides the done signal. Another model for sequential machines is the finite-state machine, or FSM. This is a state transition diagram for the 2-bit counter. While the register transfer description was structural, this is a functional description of what the counter should do. But its basic operation is the same. An increment input causes the count to be updated. When the count reaches its maximum state, it sets the done output to 1 and returns to the 0 state. Here's a Verilog description of the state transition graph. A case statement breaks out the states of the state machine. The description uses a binary encoding of the symbolic states. A vending machine is a classic example for sequential machine design. This vending machine has 3 inputs, a coin slot and 2 product buttons. It has 2 outputs, 1 for each product that's going to be vended. A finite state machine controls the mechanism to make the vending machine work. This is a simple version of the vending machine controller. We can enhance it to be more sophisticated and add more features. This FSM has 3 inputs and 2 outputs. It has 3 states corresponding to the machine holding 0, 1, or 2 unspent coins. As the customer adds coins, the FSM advances through the states that represent these different coin counts. As the customer requests products, the FSM goes back to earlier states with lower coin counts. The machine can follow several paths during operation. When a coin is inserted, the FSM moves from the none state to the 1 state. When the product 1 button is pushed, the machine vends product 1 and returns to the none state. When 1 coin and then another is inserted, the FSM moves first to the 1 state, then to the 2 state. What happens next depends on what the customer does. If the customer requests product 2, the machine vends that product and returns to the none state. If the customer requests product 1, the machine vends that product and returns to the 1 state because the customer spent only 1 coin. Since this simple machine doesn't provide a coin return, the only way for the customer to retrieve the value of the coin is to hit product 1 again. This state transition table is equivalent to the state transition graph. The left-hand columns enumerate the primary inputs and possible states. The right-hand columns show the next state and the primary outputs for each input. This is an encoded version of the state transition table. So long as we're consistent in how we encode states, the machine will operate as we expect. But different encodings may affect the size or performance of the machine's combinational logic. This is the Verilog description of the state machine. We use the parameter statement to give the encodings for the symbolic states. Thanks for watching.